All right, let's talk about a rearrangement of a conditionally convergent series and what that happens. So there are some issues with conditionally convergence that I want to talk about. So let's start with what we know. In general, let's always start with what we know. So I'm going to start off with the geometric power series, which we know the function 1 on 1 minus x equals the sum from n equals 0 to infinity of x to the n. Of course, this only converges on the interval of convergence from -1 to 1. But let's plug in some different things and play around with it and see what happens. So what if I replace all of those x's with negative x? If I do that, then of course this would become 1 over 1 plus x, which could then turn into, let's say, the sum from n equals 0 to infinity of negative x to the n, which I'm just going to replace all the x's with negative, would be 1 minus x, but this would still be a plus x squared because a negative squared turns into a positive, and then a minus x cubed because a negative cubed is negative. And then the same thing for the positive x to the fourth. So it looks like every even power was positive, etc. Okay, and then I could integrate or do the antiderivative of both sides of that equal sign to see what happens. That's another thing that I can do. And I'm going to end up with ln of 1 plus x. We're going to have all positive values here, so I'm not going to worry too much about that absolute value. And then on the other side of that equal sign, that'll become the sum from n equals 0 to infinity of the -1 to the n right here was a constant multiple. Because so it can stay, because it could have been written as, if I really wanted to, I could have had that written as -1 to the n, x to the n. That might make it easier to visualize that antiderivative. So then it'll become x to the n plus 1 over n plus 1. And then I'm going to go ahead and actually do the antiderivative of each of those terms, just because it's a little bit more visual. And that would become the x, and then minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4 plus x to the fifth over 5. And I ran out of space, sorry. So dot, dot, dot. Obviously, that can go on forever. Okay, and now this is a brand new series, which you can rearrange and rewrite it and reindex it and all kinds of fun stuff if you'd like. But I want to just realize that there is a plus c. I should talk about that really quick. That plus c, plug into x equals 0 to both sides of that equal sign, and you're going to see that all of that is 0. So your c is equal to ln of 1, which is 0. So I can now ignore that plus c. Okay, but I do want to think about the endpoints. Now, I know it's geometric, and so we already know the interval of convergence, but with this antiderivative, there is kind of a subtle difference for that interval of convergence. If I were to plug in x equals 1, then this would become, and it's maybe worthwhile to notice, if I were to plug in x equals 1, this would become 1 minus a half plus a third minus a fourth plus a fifth, and so on, which is an alternating series. You can do the alternating series test on it, and it would converge. So in fact, x equals 1 is something that it could converge. Now, it does converge conditionally, so we're going to talk about that here, but it does converge. So I'm going to plug in x equals 1. Okay, and there's going to be a little bit of a fun stuff here. If I plug in x equals 1, what's going to happen? On the left side of that equal sign, that's going to be ln of 2. Right? 1 plus 1 is 2. And then on the right side of that equal sign, I'll just rewrite it. It's the sum from n equals 0 to infinity of -1 to the n. Now, 1 to the n plus 1 for all real numbers, n is just 1. So I'm going to ignore that. And then over the n plus 1, which is the 1 minus a half plus a third minus a fourth plus a fifth forever. And now I have a value for this series, and this series is the alternating harmonic series. So now we know, let's write this down, that our alternating, I spelled that wrong, sorry, harmonic series, we have a value for it now, and that is the ln of 2 is equal to the sum. Now you can write that as the sum from n equals 0 to infinity from -1 to the n over n plus 1, and that's fine. Or you can do some reindexing. The way we typically wrote the alternating harmonic series in the past was the sum from n equals 1 to infinity of -1 to the n plus 1 over n. You can see that if I start plugging in some values here, start plugging in my counter n equals 1, and then n equals 2, and n equals 3, you are going to get that alternating harmonic series. Okay, so now I have the alternating harmonic series, and I have a value for that alternating harmonic series, which we know does converge. And if you'd like to double check some things, it does converge conditionally. Okay, so now let's do some stuff. with that. So now I'm going to kind of just rewrite that same exact equal sign down. I'm just going to skip the sigma notation. I'm going to look at the actual numbers. You can keep the sigma notation if you'd like, but I really am going to just rewrite it with the numbers. So I've got ln of 2 is equal to 1 minus a half plus a third minus a fourth plus a fifth minus a sixth plus a seventh minus an eighth plus a ninth forever. Okay. All right. I wrote that many on purpose because I really want to start to see a pattern. I'm going to write a whole bunch so we can see a pattern of what might be happening here. I'm going to take that equal sign and then just divide both sides by 2. You can do that. Whatever you do to one side of the equal sign, that's an algebraic property that I can do for, especially because this is convergent. So I can just divide both sides by 2. So I'm going to divide both sides by 2. And if I do that, I ended up with ln of 2 divided by 2 is equal to, just divide each term by 2, 1/2 minus a fourth plus a sixth minus an eighth plus a tenth minus a 12th plus a 14th minus a 16th. I'm going to run out of space, etc., etc., etc. So I can do that forever, okay? All right, now what I'm going to do, and I'm not going to do a little hand wavy with the notation. I'm not going to rewrite the whole thing, but I think we can do it. I'm just going to take those two equal signs that I have and add them together. So I'm going to add the left side of the equal sign together, and I'm going to add the right side of that equal sign together. Okay, that's what we're going to do. We're just going to add those two together. Maybe I'll make that note. We're just going to add those two equations together. And then let's see what happens. Now, on the left side of that equal sign, I'm going to end up with ln of 2 plus ln of 2 over 2. Nothing really fancy there, but there it is, which I suppose I could simplify because those are like terms, and I would end up with 3/2 times ln of 2. Cool. Okay, now let's add the right side of that equal sign, but I'm going to add it carefully. There's infinitely many numbers to add. I just want to be careful of how I add them. So I'll do it one at a time. 1 is just 1. Okay, easy enough. All right, then I'm going to do the -1/2 and the 1/2. Those ones I'm going to add together, and that just gives me the +0, which I suppose I don't need to write, but I could if I really want to. Okay, and then I'm gonna, again, be a little bit careful about how I add this. I'm gonna just write down that 1/3. So that's just a +1/3, because that's what it is, 1/3, it's +1/3. And then I'm going to add the -1/4 and the -1/4. And if I add those together, that gave me -1/2. So I'm kind of just adding some of them together, but I'm going to make sure I get all of them. So that's why I wrote this many, so we can start to see a pattern. I am going to make sure I get all of them. Let's do the next one. So that got to the 1/4. The next one I'm going to do, yeah, -1/4, sorry, plus -1/4 is -1/2. The next one I'm going to write down is just the +1/5. Just so I don't lose it. It's just the +1/5. And then the next one I have is -1/6 plus 1/6. Those will cancel, and that will be a +0. I suppose I don't need to write the +0, but it's there. If you want, you can write it or not. I'll leave it there, but you're gonna want to not write it eventually. Okay, let's keep going, and I'm gonna just add the 1/7 so I don't lose it, which is just plus a 1/7. And then again, I'm gonna do the -1/8 and the -1/8. When I add those two terms together, I'm going to get a -1/4. So that'll be the next thing that I have. I'll write that down, the -1/4. Okay, we got it. Let's keep going. I'm going to write down the next one that I have. I'm just going to write down the 1/9 so I don't lose it. So the +1/9 so I don't lose it. Now I'm kind of ran out of terms at the top at least. So I have to do a little bit of yoga for the brain and imagine what that next term is going to be. That next term was going to be a -1/10 and the 1/10, which could be gone. So those are going to be gone. I'm not going to write that +0 anymore. The 1/10 and -1/10 are gone. But then I'm going to notice, if you see that, I'm going to have also a 1/11th over there, right? Like way over there off to the side. Like that's hard to see. I'm so sorry. There's going to be a 1/11th over there. So I'm going to just not lose that, the plus the 1/11th. And then you can notice, if you kind of do a little yoga for the brain there, you should be able to notice that way past that is also going to be a -1/12. So a -1/12 and the negative 1/12 over here, there is going to be a negative 1/12 next, and I can add it with this negative 1/12, and that will give me, and I'll write it down so I don't lose it, the negative 1/6. Okay, I've totally run out of space. So let me do a little dot, dot, dot there. But you can imagine I can do this all day long, right? Like literally forever. Let's rewrite this because we got a lot going on. Let's rewrite it and simplify some things. This is going to become 3/2 ln of 2 is equal to 1. I'm going to stop writing that plus 0. Okay, it's gone. Plus a third. And then I have minus a half plus a fifth. I'm not really sure why I chose a different color for that fifth. Okay, it was just a fifth. Sorry. Okay, and then I have a plus a seventh, and then minus a fourth, plus a ninth, plus an 11th, and then minus a sixth. And it would be then come plus a 13th, and then plus a 15th, and then minus an eighth. So you might notice that pattern, and you might want to pause and list out more terms yourself to see if you can find the pattern yourself of which terms you're adding. But you should see that I got a positive, and then a negative. A positive, and then a negative. A positive, and then a negative. And the negatives were all the evens. The even denominators, I should say, the numerators were all 1. The negatives were all of the even denominators, and the positives were all of the odd denominators. That takes care of all the even numbers, all the odd numbers. They're going to all be there. If you recognize that pattern, you might want to pause and write more, but you can see that that does take care of all of them. So this right here just is a rearrangement of the alternating harmonic series. That's what this is. This is a rearrangement of the alternating harmonic series, and I rearranged it as a positive, positive, and then a negative. Positive, positive, and then a negative. So that means that it really is just a alternating harmonic series, which is the sum from n equals 1 to infinity of negative 1 to the n, n plus 1 over n. It was just a rearrangement of it. So we have this kind of interesting phenomenon that happens, which is we started off with figuring out a value for the alternating harmonic series. We figured out that the alternating harmonic series converges to the number ln of 2, which is a number. It's like 0.8 or something. It doesn't matter. It's a real number, though. It is. ln of 2 is what I got for the value of those infinitely many terms. But that ln of 2 was the value when I added them in this order. So because of this conditional convergence, the rearranging actually changes the value. There's infinitely many terms, but the rearrangement changed the values because the conditional convergence was really all about the fact that without the negative, this whole thing would have shot off to infinity. So if I change that, the positive and negative, then things change quite drastically. All right, so it's kind of cool. Now we have 2 different values for the alternating harmonic series. That does not mean that ln of 2 equals 3/2 ln of 2. That's not true. That's not what that equals. This is an infinitely large series that is conditionally convergent, so a rearrangement changes the values, and so I ended up with a different value for that alternating harmonic series. And then something else that's kind of cool that's just way beyond the scope of this class is I could have done that for any number I wanted over here. I could find some rearrangement of the alternating harmonic series to get 5/2 ln of 2. I could find another rearrangement to get 3. Not ln of 2, but just 3 if I really wanted to. Like, you can kind of play around with it. It's definitely beyond the scope of this class, but it's an interesting thing to think about, which is really what comes down to this conditional convergence being so important. You really want something to be absolutely convergent to get a single value. The conditional convergence is risky. All right, just thought that was cool. I know we didn't have time to cover that in class, so I hope that helps you guys see something interesting. Thank you.